Xeon 6 for workstations is launching. And I'm very excited by this because I really like the 6980p. I covered that last year. The 6980p, 12 memory channels, kind of a game changer. The Pro WS W890E Sage SE, it's kind of a mouthful for a motherboard name, isn't it? It's here. And this is the chariot for this. This is the 658X, the Xeon 6. X, it's unlocked, as indicated by the box. And workstation, and so we're doing that. This is fun. This is Intel's answer to Threadripper, which we'll have to benchmark and do all that. But first I have to build a system, and we have to unpack this. Dual 10 gigabit PCIe 5 out-of-band management. It's a server, but in a workstation, or a workstation. It's hard to tell the difference anymore. Let's take a look at our motherboard and get our build started so we can get to the benchmarks. Okay, first off, what is this? What is this madness? Right in the box. This is a fan for the memory. You see, we have done some videos. We actually kind of broke the news that DDR5 was throttling a lot in workstation contexts, or not at all, as was the case in some cases. And so Intel noticed the same thing. And in this refresh, in this build, ASUS and Intel have said, yes, we need to fix that. This mounts on the motherboard to provide direct cooling for the memory. And these fans are pretty serious. We'll see how that works out noise-wise and all that in the build. So you can skip ahead with the chapter markers, or we can go ahead and unbox the motherboard. Also, in the box is the motherboard, which I will get to in just a second. I'm really excited by this motherboard because it's like kind of a return to ASUS quality, build quality, in my opinion. It is a substantial, hefty motherboard. Okay, in the box, there is a BIOS license sticker. Cool. ASUS Control Center Express, Quick Start Guide Manual. And then we have our second power supply adapter. So this can run dual power supplies. We have our DisplayPort adapter. So this has Thunderbolt. And so you can take DisplayPort out of your graphics card back into the motherboard and then out again via Thunderbolt, which is actually kind of important. Some people in our forum run like the Dow Corning Thunderbolt extensions, and so they'll have their fancy fire-breathing workstation in the basement, but then they'll have a Thunderbolt cable, an optical Thunderbolt cable that runs from the basement to their workstation upstairs, like where their monitor, keyboard, and mouse is. And so this is fantastic because this lets you tunnel, you know, your RTX Pro 6000 or your R9700 AMD or whatever it is for your workstation graphics card through that Thunderbolt connection, because it goes out from the GPU back into the motherboard, and then it's encapsulated into Thunderbolt and back out again. I'm only so verbose about that because we get a lot of questions about that on the forum. A lot of people just expect it to work without the display connections. Like, no, you physically are going to have to route those display connections. There's not really a path through the motherboard to do that. We've also got some mounting hardware for our LGA. This is 4710-2, I think. So it's a different socket than Xeon for servers. We also got some thermal pads. Some M.2 mounting hardware. It's a fairly elaborate M.2 setup we'll go over in just a minute. Got an analog temperature sensor that you can mount wherever. And you get two SATA cables. So there's kind of a lot of accessories in here. LGA 4710-2, I mean. You're going to need 10-2 for the 220 circuit this thing's going to require. The electricians are laughing at that one. Now, this motherboard has some important features. There's actually two versions of the W890 Sage. I don't know why ASUS decided to call both of them Sage. This is the real one. This one has 8 memory channels. The other one only has 4 memory channels. This one has a bunch of PCIe slots. The other one only has 4 PCIe slots. It's not a different chipset. AMD on Threadripper, you know, they have TRX 50 and WRX 90, but you can use a Pro CPU and a non-Pro motherboard. Intel did the slightly less confusing thing in that the chipset just works for whatever you want to do. It's up to the motherboard maker to decide how they want to use the W680 chipset. In this case, ASUS has decided to call both boards the Sage. Last generation, they had the Ace and the Sage. The Ace was the 4 memory channel platform. The Sage was the 8 memory channel platform. This one, the Sage W890E, E means enterprise, I think. And this is the one you want for 8 memory channels. And 8 memory channels is definitely really important on the whole Xeon this go around, but we'll see that in the benchmarks. Next up, your power supply. this helpful sticker explains how to hook it up if you're going to use single or dual power supplies. For single power supplies, you're going to need 2 PCIe 8 pins plus 2 PCIe 8 pins. They're different. One of them has 4 12-volt lines, 4 12-volt cables. The other one has 3 12-volt cables and some sense pins. The PCIe style connections go here, and then you have 8 PCIe connections that go here at the top. So the gray connections at the top, one of them is CPU style and the other one is PCIe style. Don't force the connections. They are physically different connectors. The one connector has 4 12-volt lines. The other one has 3 12-volt lines. And so you want to pay attention to that. It tells you on the silk screen which one is which, and it also tells you on this little sticker which one is which. And the colors here that ASUS chose to use for the power connectors don't really make any sense because you've got the ATX 12-volt style connector. It's 4 12-volt wires versus the PCIe style. That would have been a good distinction for the colors, but that's not what's going on here. So pay attention to the sticker. We have 7 expansion slots, X16, because you've got all the PCIe lanes on this platform. You've got one M.2 that is PCIe Gen 5 here. This is a great for your, like a PCIe Gen 5. Those run a little hot. This is a much better heatsink arrangement than previous ASUS boards. I had a little trouble maintaining thermal control in previous configurations with ASUS with this front M.2. So ASUS has really beefed that up. You've also got more M.2 ports under here and here. So you can rock a lot of M.2. So it's a total of 4 PCIe 5 M.2. One here, 2 here. Now, if you've got a lot of GPUs, then these will be covered. This one is going to breathe a little better. That's fine. You may also notice the SlimSAS connections at the front. That goes through the chipset. So that's not direct PCIe lanes, but they're PCIe 4 by 4. But this motherboard does have an 8-lane MCIO connector. Thank you, ASUS. MCIO is exactly what the doctor ordered for these high-end platforms. And there's an 8-lane MCIO connector here. So you could run 2 M.2 off of that, or an 8-lane peripheral, or use it in whatever fun custom thing you want to do for your workstation. So in my opinion, ASUS has done a great job with the PCIe layout options on this board. We get a micro SD card slot for the BMC, a lot of other BMC options. There is an eKey M.2 here if you want to add Wi-Fi. That's not built in, but it is an option on this board. We've got a ton of 4-pin fan headers scattered all around the motherboard for any kind of exotic cooling that you want to do. And it also has 4 SATA ports. We have a single USB Type-C header, and we have a single 5 gigabit front panel USB header, 2 USB 2 headers at the bottom edge, an RS-232 serial header, TPM, and all the stuff that you would expect, and a number of LED headers. You'd be surprised how many people wanted LED headers on workstation boards. Like, it's kind of nuts. ASUS did some workstation boards that had no RGB whatsoever, and there were complaints. I can hardly believe that. You should engage below if you and let us know how you feel about RGB headers on workstation motherboards, because I don't know how to feel about that. And that's just to give you an idea of how our DIMM cooling is going to go. It is a forced downdraft over the DIMMs. This cooling does make a tremendous difference. You're running, 24, 32, 48, 64, 128 gig DIMMs on this platform. You really do need active cooling. It's astonishing. A lot of the major system builders, like Dell, HP, Lenovo, they're building special shrouds to duct cooling, and it was kind of missed last generation that DDR5 needs that in a DIY, so that ASUS and Intel are rising to the challenge by incorporating the design into the motherboard. Kudos. We needed that like a generation or 2 ago with DDR5. So very nice to see. Oh, one really pro tip, if you're building a system with this, make sure that the switch configuration matches what the defaults are in the manual. Sometimes with packing or unpacking, you could accidentally flip the switch. I've seen these have the wrong switch settings out of the box. So, and that's been a quick tour of the motherboard, but we need to get this thing built. I need to do the benchmarks. I need to see how this CPU is going to perform. Okay, in the spirit of bottom line up front, the Intel Xeon 658X is a good 24-core chip. But if you're focused on the per-core performance in this tough competitive landscape, I suspect you're going to be disappointed. And yet, I don't think you should be. The Xeon 658X is one of the most interesting workstation CPUs that Intel has made in years. The 24-core CPU can outclass a 9995 WX Threadripper by 25% for memory performance and match it for PCIe lanes and speeds. I mean, from Intel, we've probably never seen this much gen-on-gen power efficiency improvement per core in the entire history of the company. I mean, that's right. This 24-core 658X Xeon 6 workstation is just 24 cores and 48 threads.
but that's all that's needed to saturate an 8-channel memory config. Officially, it supports DDR5 6400, 128 PCIe 5 lanes, 144 megs of cache, 250 watts base power, 300 watt boost. It's roughly $1,800 in price. In real world performance on our ASUS platform, I didn't find an upper memory bound for memory overclocking and bandwidth. 500 gigabytes per second is possible on this platform. Peer-to-peer PCIe bandwidth is also top-notch, which, again, big improvement for Intel. But I feel like I need to explain how I see the competitive landscape and the trade-offs here in terms of raw performance versus platform features. Intel is uniquely positioned with these new Xeon 6 parts. So let's go a little deeper. What exactly is the Xeon 658X in the system behind me? It's a Xeon 6, but workstation CPU. Think 6980p, but now in desktop form. It's a single socket workstation part. This one has 24 performance cores, 48 threads, 8 channels of DDR5 6400, and support for up to 4 terabytes of memory, 128 PCIe 5 lanes. The power, the boost, 300 watts of boost. You can have unlimited boost on our ASUS motherboard. 4.9 gigahertz max boost, although I could do 5.1 with an overclock, thanks to our Silverstone 360 AIO. Design-wise, this is a very different moment for Intel versus the Sapphire Rapids Refresh Xeon W3500 series CPUs. Those older workstation parts topped out with, 4,800 mega transfers on their 8 channels and 112 PCIe 5 lanes. They're still big iron workstations, don't get me wrong, but Granite Rapids moves the platform in exactly the places that workstation builders will notice. More memory speed, more PCIe, much better generational scaling and throughput, and the power efficiency. The power efficiency is really amazing. Intel dumped infinite energy into Sapphire Rapids, and that isn't the case here. In a competitive landscape, you of course have Threadripper. And there is a 24-core Threadripper, both in Pro and non-Pro. The Pro Threadripper CPUs give you more PCIe lanes and 8 memory channels versus 4 memory channels in regular Threadripper. 24 cores, 8 memory channels is a capacity play, not bandwidth. You see, AMD's design is a bit weak here. If you need at least 48 cores to take advantage of 8 memory channels, then 8 memory channels on 24-core CPU on Threadripper is really just about capacity. In other words, AMD's design with 24 cores you can't really take advantage of the speed that 8 memory channels could possibly give you on the Pro platform. Intel, their CPU, the 658X here, is priced like a non-Pro Threadripper. It's about $1,000 cheaper than the Pro 24-core Threadripper, but even the 9995WX 96-core Pro Threadripper can only deliver about 75% of the memory bandwidth we see from this much more modest 24-core CPU. So think about that. As you put your workstation together, certainly community builders in the Level 1 text forums have been annoyed, I think, from the segmentation that AMD has done in this way. Even if you opt into the Pro platform, the less expensive Pro CPUs can't really keep up with the rest of the platform. This is the key distinction that I really want to hammer home. This is not Intel's answer to the biggest and baddest Threadripper. Threadripper is still generally the core performance king. And for most general purpose workloads, yeah, Zen 5 is going to be awesome. But nevertheless, Intel is making a very strong case that if what you need is platform capability per dollar, memory bandwidth, PCIe expansion, accelerator connectivity, lots of storage, lots of network, multiple GPUs, you do not necessarily need to jump on a $5,000 to $10,000 CPU to get there. This is proof. Let's get to the benchmarking.
Starting the benchmarks with code compilation. It's like, oh, but I would remind you this is a 24-core, 48-thread part. And everything else that we're looking at here for comparables, is 16 to 32 to 64 cores. I don't have a 24-core Threadripper. I tried setting the 9970X to be 24 cores, but then I got really squirrely behavior. So let's not do that. 215 seconds for time to LLVM compilation. So not quite as good as the 32-core 7970X, but not quite as good as the 3990X from last generation, but better than the 16-core parts and better than the Core Ultra 9 285K. But again, this is just down to how many cores you got, because it's really not all that bandwidth intensive most of the time, at least until everything gets cached. LLVM is basically the same story. Godot compilation, 123 seconds. I mean, this isn't bad for a 24-core part. I have a feeling like the 32 or the 64-core part here would be smoking fast, especially because of the memory bandwidth. But 24 cores for code compilation, it's kind of holding us back.
Same story with Gem 5. It's just a hair faster than the Core Ultra 9 285K, even despite having 8 memory channels versus 2.
Once I started benchmarking, the thing that stood out immediately was the 658X is not just a little better than Sapphire Rapids Refresh. It feels better behaved. In my testing, single-threaded and lightly threaded performance is only about 5% higher than the Xeon W3500 generation, and that by itself is nice, and I might have expected more when I compare the two. But then when I looked at power usage, then the numbers made sense. The headline is multi-core efficiency. Under sustained load, I'm seeing something like 50 to 60% better performance per core versus Sapphire Rapids Refresh when we're fully loaded, because it's at less power. On the older chips, a lot of things that, a lot of the single core performance that comes from the platform is pouring all the available power budget into just a handful of cores and then letting them boost aggressively, and then falling off as the load spreads out or you get more cores that are loaded. That's the old system administration mantra. It's like, oh, you get a new box, you go into BIOS, you disable all the power management, and you try to beat the scheduler into giving you the performance you want. Granite Rapids feels like the opposite philosophy. The cores simply do not need as much power to deliver. They don't need any power or drama or configuration, they just work. And honestly, Intel engineering deserves some hype here. This might be one of the biggest gen-on-gen efficiency improvements that Intel has ever delivered in a workstation CPU. And that's why we don't see as much uplift in absolute top-line performance, because we're not dumping 500 watts into a couple of cores anymore. We're getting the same performance at less than half power from one generation to the next.
Our build 2 time to compile is a respectable 67.96. Not bad, again, for a 24-core part. It's coming in similar to our 32-core 7970X from last generation, which is kind of a pattern that we'll see in a lot of benchmarks in this. If you just look at the benchmarks of small models and, running on local score and running on CPU, that is mostly a CPU core dominated story. And you look at this and it looks brutal for Intel. I mean, look at this. It's like the 24-core part is falling well behind, last gen Zen 4 parts for Llama 3.1 Instruct Q4 on the local score benchmark. It's like this does not look fabulous, but this is also misleading. IKllama.cpp has better CPU optimizations, AMX and all this other sort of stuff, but even without IKllama.cpp, which will even give you a little bit better performance, if you look at the larger models, like a 32 billion parameter model, it's like, okay, even in local score, it's like, it's coming up. Okay, the larger model is starting to take advantage. The more memory bandwidth is dominating over the lack of CPU cores that we have for this comparison. And we're getting similar scores here because there's other limitations in the platform. There's almost no difference moving from 32 to 64 cores because the bottleneck is elsewhere. Well, here on the Intel Xeon, the bottleneck is not that we have enough cores. The bottleneck is that we don't have enough cores, but we have more memory bandwidth in the other platform, and so the story starts to change a little bit. And if we switch our backend, here's CPU with the basic linear algebra system as a backend using Llama 3.1 in Q8. So this is an 8 billion parameter model now, down from 32 billion, but in Q8, and wow, the 658X really starts to stretch its legs, 29.02 tokens per second. And this is CPU inferencing. This is CPU inferencing on an 8 billion parameter model with llama.cpp. 258 tokens per second for prompt processing on the same model, which again is significantly faster than anything else in our chart. More than twice as fast. And our 24 core here for text generation with the Granite 3.0 3 billion A800M Instruct Q8. 99 tokens per second are the leader in our chart here. And for prompt processing, it holds its own with our higher core count Threadripper counterparts. Not bad, but again, this is a smaller model. It's only 3 billion parameters in Q8. Mistral 7B Instruct in Q8 for text generation, 31 tokens per second versus our next best 22.5. This is a really good showing from Intel. I mean, this is really... They've like AMX and for like CPU inferencing, there's a story here. Pat Gelsinger was right again. It's like CPU is going to be back. Not this. I mean, it's useful to be able to run CPU tasks, like AI tasks on CPU, but also CPU tasks running tasks that were created by an AI agent. This dovetails with that really nicely. So there's a really interesting story there. Twice the speed for prompt processing. And so yeah, if we side by side that with the llama.cpp, we can see, oh, the 24 core is really showing some incredible performance here. This is Llama 3.1 8 billion Q8. with a Blast backend. OpenVINO is another fun one. I mean, OpenVINO, it's Intel. Does anybody expect Intel to not do well? And 122 versus 147, 24 cores versus 64 cores. Intel's doing well here. Person detection and FP16 on device CPU. 24 core even manages to pull ahead of the 64 core part. Pelibos 2.3 with a grid size of 500. Again, the 24 core part is holding its own. High performance conjugate gradient, 31 versus 24. I would have expected Intel to do a little bit better in Reliant, but it's not bad, again, considering 24-core CPU. For Mini FE 2.2, the result here was a little surprising. Intel wins by a wide margin with a 24-core part. GPAW 25.1 for the carbon nanotube. This kind of makes sense being CPU bound. It's pulling ahead of the 7970X, but worse than newer or higher core count parts. The Cloverleaf 1.3 benchmark, 36.46. Surprisingly good result here. Cloverleaf BM16, 319 versus 537 again. Kind of a surprising result, but good. A good surprising result. X Compact 3D and Compact 3D, 193 cells per direction, 19.45. Very, very respectable for a 24-core part. Open foam in 22 seconds versus 16 seconds for a 64-core part. I have a feeling that the Intel like 32 and 64-core parts are going to do good. Are going to do really well here, but I got to get my hands on some. Algebraic multi-grid benchmark. Yeah, 658X. This is got to be an AMX related thing, right? Pennant 1.01. Not a bad result here for 24 versus 64 cores. If Intel's result scales even remotely linearly, Intel's got a pretty good set of Xeons this generation. Radinia 3.1. It's a respectable result for a 24-core processor. I feel like I'm going to be saying that a lot. You can check out the full benchmark results in a link. It really isn't bad for a 24-core part. I mean, NAS parallel benchmarks 3.4, class BT.C. I mean, that's a really good result for a 24-core CPU. Total MOPS per second, more is better. Yeah, 24 cores. It's like it doesn't look quite as good there, but it's holding its own with a 32-core processor. It's pretty good. CPU-bound encoding is pretty strong. You look at the graph, and it might not look like it, but this is a pretty good result, again, considering 24 cores. Given the memory bandwidth, I was curious about web service type workloads. So Nginx, 24 cores, it's holding its own with the 32-core Zen 4 part. Not really as memory bound as I thought it would be. Memcached is like, oh, that'll be memory bound. Not really, not so much. It's more core bound than anything. But still, that's a pretty good result for a 24-core processor. If we look at the geometric mean of all of our blast tests, the 658X comes out on top. Gee, I wonder why. Could it be the AMX extensions? And the memory bandwidth? Yeah, I think so. So if you dig into these benchmarks, you'll find that the individual core performance is about 5 to 7% over Intel's last generation. And the Xeon testing, this like the Xeon 6, the 12 memory channel platform that we tested last year, we sort of found it's like, yes, this is handily better than AMD's Zen 4 parts, but it falls short a little bit of the Zen 5 parts, except in cases where Intel can leverage some of their special sauce like AMX. In this case, this is an update to the Xeon 6 stuff that we saw in server CPUs, and Intel has improved things a little bit in terms of, this is an 8 memory channel platform and some other updates like that. So the core performance here is a little bit better, the power budget is a little bit different, and the memory bandwidth is very much improved from last generation. And so things that can use AMX and things that benefit from memory bandwidth, like larger AI type tasks, really run well with this platform. And that combined with the I/O thing, make this a compelling platform in relatively low core counts if you want 8 memory channels for both the capacity and performance play. I would have loved to have seen more performance uplift per core, but the efficiency per watt is there. So these use way less power than the last generation, in other words, even while still giving you a 5, maybe 10% in some workloads performance boost. But it's in that 5% range that we see for the per core uplift, and it can't quite match the raw performance of Zen 5. And I think that's why Intel was maybe a little shy releasing these Xeons. But nevertheless, there's a lot to be proud here of, and like this is a very respectable and very aggressive in some ways number 2, and number 1 for specific workloads. So Intel leaning into those workloads, I think they'll find some customers for those specific workloads. General purpose might be a little bit more of a challenge. It depends on if you know your workload.
So you might think some of the benchmark results are a little puzzling. That's the other piece of the story here. It's the memory bandwidth. So that's why some of the performance here is bananas. The 658X officially supports 8 channels of DDR5 6400. If you do the math, it's about 409 gigabytes per second theoretical peak bandwidth. 8 channels times 6400 mega transfers per second, 8 bytes per transfer. This is not desktop fast. This is workstation and server class bandwidth. And that is one of the reasons that this chip behaves the way that it does in some of those benchmarks. The official support is right there in Intel's spec sheet. 8 memory channels, 6400 mega transfers per second. And that's JEDEC. This is also where people need to separate workstation memory from gamer memory. DDR5 6400 on a gaming platform, like a gamer DDR5 versus 6400 JEDEC RDIMM memory workstation is just not really the same conversation. Consumer memory marketing is usually around tight timings and high transfer rates and a 2 or a 4, maybe a 4-channel context. This platform is about total throughput across 8 memory channels with ECC RDIMMs and platform stability and serious capacity. What really got my attention though is that this platform looks like that it has room to run. So beyond 6400, 7200, even 8000 and 9600 is possible on our ASUS W890E platform. At 7200, what I tested, the theoretical max bandwidth is about 460.8 gigabytes per second, 8512 gigabytes per second, or 600 gigabytes per second for 9600. This 24-core CPU can do over 500 gigabytes per second with the faster memory. That's not fantasy, that's just the math and this platform, I think. Now, for my own testing, I'm hitting about 430 gigabytes per second with DDR5 7200, and that was pretty easy with latency down around 80 nanoseconds. And that matters because it's not just from the spec sheet, like that's what the system is actually delivering. It's moving enough data to make high core count alternatives look way less balanced than you might expect. And seeing those kind of numbers from a 24-core platform is what surprised me, because normally with AMD, you need more than 24 cores to do that. Intel's 24-core part looks comfortable achieving nearly 400 gigabytes per second with JEDEC 6400 and beyond 400 gigabytes per second with just a little bit of fiddling on my end. So that tells me that the memory controller and I/O plumbing here are doing the real work. Same story does show up in PCIe. So I did peer-to-peer testing with 4 RTX Pro 6000 GPUs, and this is just another piece where the newer platform feels like a real generational step. Now remember, on Sapphire Rapids refresh, I was only seeing about 30 gigabytes per second between cards. That's less than half of the PCIe Gen 5 bandwidth. But here, 63 gigabytes per second, real world. At some point, the bottleneck is no longer the platform. And the fact that this is 24 cores, again, I think, the wrap up here is Pat Gelsinger was right once again. People rolled their eyes when he said CPUs were coming back to the forefront for AI and other workloads. Where people were just talking as if the CPU is there to babysit accelerators. But that's not how modern workstation and AI systems actually behave in 2026. With multi-GPU systems and agentic workflows and data preprocessing orchestration, inferencing pipelines, storage movement, running AI tasks on the CPU, memory-heavy tasks, the CPU matters a lot more than it has in the past couple of years. So what Intel has done here is build a workstation platform where the CPU, the memory subsystem, and the I/O all feel pretty well balanced. The per-core performance and multi-core performance at least matches Zen 4, and you're pretty close to Zen 5 in a lot of cases, except for workloads that benefit from AMX, and then you'll get a pretty substantial performance boost, which AI workloads can use that. So the best thing about this platform is that the 24-core SKU makes me want a bigger CPU and not a different platform. Usually with a lower core count workstation chip, you hit the limits of the CPU before you hit the limits of the platform. That doesn't seem to be the case here. And that completely defied my expectations, which is why I'm excited. After seeing what this 24-core part can do, I really want to see what happens when Intel scales this and scales it a little bit beyond here, 7200 memory and beyond. It's just that those kinds of things are pretty unobtainable right now because they're going to the more expensive stuff in AI workload land and whatever. So this is just me using the stuff that I already had, mostly testing and everything else. So yeah, lots of fun. For the memory, I tested it with SK Hynix JEDEC pretty much across the board. And then we also reused our G-Skill kits in 6400 and 7200 that I already had. And the 7200 G-Skill kit, like there is no, even overclocking beyond 7200 was possible. And yeah, pretty nuts. I modeled this level 1. If you have any questions about the 658X or you want to see a particular thing benchmarked, hit me up in the forum. Let's work it out. I'm signing out and I'll see you there.